Right now, somewhere on Earth, a storm is building. Warm air is rising silently from the ground, moisture is gathering in great invisible columns, and deep within a towering cloud, the first spark of electricity is about to ignite. You cannot see it from here, but somewhere far away, the sky is beginning to speak. Tonight, we explore the extraordinary world of storms. From the gentlest rainfall to the most ferocious hurricanes, from the crack of thunder to the silent glow of sprites flickering above the clouds, storms are the atmosphere expressing itself with all its restless power. Welcome to Drowsy Discovery. Over the next 2 hours, over 100 gentle facts will carry you through the world of storms, drifting softly from one wonder to the next. There is nothing to memorize, nothing to remember. Just listen and let your mind drift. Have you ever fallen asleep to the sound of rain against a window, feeling perfectly safe while the world outside rumbled and rolled? You are not alone. If these gentle journeys bring you peace, consider subscribing or leaving a quiet thought in the comments below. It helps others find their way here too. Now let your shoulders soften. Let your breath slow to its own natural rhythm. Feel the surface beneath you holding your weight and allow yourself to sink a little deeper into this moment. The storm outside can wait. Here, you are safe. Let us begin. Every storm begins with something invisible, the quiet warming of air. When sunlight warms the ground, the heated air above it becomes lighter and begins to rise, climbing through the atmosphere in great invisible columns. As it ascends, the moisture it carries condenses into tiny droplets, forming clouds that thicken and billow ever higher. This process, called convection, is the engine behind nearly every storm, from the smallest afternoon shower to the most violent supercell. It is driven entirely by heat, moisture, and gravity, three of the most fundamental forces in the natural world. The next time you feel warmth on your face, consider that somewhere the same warmth is lifting air skyward, silently sowing the seeds of a storm. Every tempest begins with a whisper of rising heat. The atmosphere holds enough energy in a single thunderstorm to power a small city for days. A typical thunderstorm releases energy roughly equivalent to a small nuclear power station running for several hours. Most of this comes not from lightning, but from the condensation of water vapor within the cloud. When vapor turns to liquid, it releases latent heat that fuels the updrafts, keeping the storm alive. The electrical energy of lightning represents only a tiny fraction of the total budget. The vast majority is spent lifting millions of tons of air and water, reshaping the sky in real time. If all that energy could be captured, it would supply a small city with electricity for days. Storms are among the most powerful events on the planet, and they happen constantly. A storm cloud can weigh more than 6 billion kilograms and still float in the sky. A large thundercloud contains roughly 500,000 tons of water, and when you include the mass of the air within it, the total can exceed 6 billion kilograms, yet it floats. The water exists as billions of tiny droplets and ice crystals so small that they fall at an almost negligible speed, while updrafts rising at over 100 kilometers per hour support these particles and push the cloud higher. It is a balancing act between gravity pulling downward and air pushing upward, sustained as long as the storm has energy. A storm cloud is taller than most mountains, heavier than a fleet of ships, yet held aloft by nothing more than moving air. A temperature difference is all it takes to birth a storm. The atmosphere is rarely uniform. Pockets of warm air sit beside cooler masses, separated by invisible boundaries called fronts. When they meet, the warm air rises over the cooler air, and as it climbs, its moisture condenses. You may have felt that strange stillness before a storm arrives, the air itself seeming to hold its breath as these invisible forces gather overhead. This collision is one of the primary triggers for storm formation, particularly where warm tropical air meets cold polar air. The greater the temperature contrast, the more violent the lifting, and the more severe the storm. Some of the most ferocious weather events in history were born along these sharp thermal gradients. A storm is the sky trying to find equilibrium, nature's way of smoothing out what has become uneven. Most storms are born where the ocean surrenders its heat to the sky. The tropical oceans are the nurseries of the world's most powerful storms. When the sea surface rises above roughly 26 degrees Celsius, warm water evaporates rapidly, feeding moisture into the air above. This moisture-laden air rises, cools, condenses, and releases latent heat, drawing in more moist air from below. The cycle feeds itself, and when conditions align, it spirals into a tropical storm or hurricane. Without the ocean's warmth, these storms could not exist, because it is the continuous supply of evaporated water that sustains them. When a cyclone moves over cooler water or makes landfall, it is cut off from its fuel and weakens. The ocean gives, and when it stops giving, the storm fades. The spinning of the Earth determines which way every storm rotates. Because the Earth rotates, any fluid moving across its surface is deflected, to the right in the northern hemisphere and to the left in the southern. This deflection is the reason storms spin rather than blow in straight lines. As air rushes toward a low-pressure center, the Coriolis force bends its path into a curve that organizes into the spiral structure defining cyclones and hurricanes. In the northern hemisphere, storms rotate anti-clockwise. In the southern, they spin clockwise. Near the equator, where the effect is weakest, tropical cyclones rarely form because there is not enough rotational force to organize the winds. It is a subtle influence you would never feel standing still, yet the spin of the planet shapes the spin of every storm. Storms are the atmosphere's way of redistributing heat from the equator toward the poles. The tropics receive far more solar energy than the poles, and without a mechanism to move that excess heat poleward, the equator would grow ever hotter while the poles grew colder. Every thunderstorm, hurricane, and winter gale is part of a vast transport system shifting warm air toward the poles and drawing cool air back. The jet streams, trade winds, and mid-latitude storm tracks all participate, moving heat and moisture across thousands of kilometers. Even the most destructive storms serve a purpose essential to climate stability. Without them, temperature differences would be extreme and conditions for life very different. Storms are the breath of the planet, exhaling warmth toward the cold places of the world. And within every storm, there is a phenomenon so fast, so bright, and so powerful that it has captivated human minds for millennia. A bolt of lightning is 5 times hotter than the surface of the sun. When lightning arcs between a cloud and the ground, the narrow channel of air is heated to roughly 30,000 degrees Celsius, nearly 5 times the temperature at the sun's visible surface. This heat is produced in a fraction of a second as an enormous charge surges through a pathway no wider than a thumb. The surrounding air explodes outward in a shockwave we perceive as thunder, and the light you see is the glow of superheated plasma existing for only milliseconds before it fades. If you have ever watched a storm from a safe distance and felt the warmth of a nearby strike, you stood in the presence of temperatures hotter than a star. Lightning is one of the most extreme events in the natural world. Lightning travels at nearly 1/3 the speed of light. The return stroke of a lightning bolt, the brilliant pulse of light you actually see, travels from ground to cloud at speeds approaching 100,000 kilometers per second, roughly 1/3 the speed of light. The initial stepped leader, the invisible surge that carves the path, moves more slowly at around 200,000 meters per second, descending in short branching steps. When the leader connects with an upward-reaching streamer from the ground, the circuit completes, and the return stroke flashes upward in an explosive surge. The entire sequence unfolds in less than a second, involving billions of electrons cascading through air, briefly transformed into a conductor. Lightning is a conversation between sky and earth, spoken in millionths of a second. Thunder is air, expanding faster than the speed of sound. When lightning heats the air to tens of thousands of degrees in a fraction of a second, the air expands so violently that it creates a shockwave, the thunder we hear. Close to the strike, it is a sharp crack, but at a distance, it becomes a rolling rumble, because sound from each section of the bolt reaches your ears at slightly different times. Since sound travels at roughly 340 meters per second, counting 5 seconds between flash and rumble equals about 1.5 kilometers of distance. On a still night, thunder can be heard up to 25 kilometers away, a deep voice echoing across the landscape. It is the atmosphere speaking aloud. The average thunderstorm produces enough electricity to power a household for an entire month. Each lightning flash carries roughly 1 to 5 coulombs of charge and delivers about 30,000 amperes, though for only a few millionths of a second. The total energy in a single bolt equals 1 to 5 billion joules, enough to run a household light bulb for months rather than minutes. A typical thunderstorm produces hundreds or thousands of flashes, so the cumulative energy is enormous, greater than what many small cities consume in an entire week. However, lightning is far too brief, unpredictable, and intense to capture practically. The energy arrives in microsecond bursts that make storage almost impossible with current technology. Still, the sheer power flowing through a single storm is humbling, a display of nature generating forces that dwarf anything human engineering can yet replicate. Lightning strikes the earth roughly 100 times every single second. At any given moment, roughly 2,000 thunderstorms are active somewhere across the planet, collectively producing about 8 million lightning strikes each day, which works out to roughly 100 every single second. Right now, as you rest here quietly in the darkness, bolts of lightning are arcing through clouds over tropical forests, over distant oceans, over mountains you will never see, illuminating landscapes where no human eye is watching. The majority occur in tropical regions where warm, moist air fuels the strongest electrical charges within towering cumulonimbus clouds, with Central Africa, the Amazon basin, and Southeast Asia among the most lightning-prone areas on Earth. Over the open oceans, lightning is less frequent because the smoother, cooler surface produces less turbulent updraft activity. The planet is wrapped in a constant, invisible web of electrical discharge, so frequent and so widespread that it forms a measurable global circuit between the surface and the upper atmosphere. The longest recorded lightning bolt stretched over 700 kilometers across the sky. In 2020, the World Meteorological Organization confirmed a single flash extending over 768 kilometers across the southern United States, from Texas to Mississippi, crossing through multiple states in less than a second. This mega flash shattered all records and revealed how far lightning can travel under the right conditions when the atmosphere cooperates perfectly. Megaflashes occur within large mesoscale convective systems, where vast sheets of cloud provide a continuous medium for the discharge to propagate horizontally across enormous distances. Unlike vertical bolts in local thunderstorms, these flashes travel through the upper cloud layer, sometimes illuminating the sky for hundreds of kilometers with a single brilliant pulse. A single flash of electricity can span a distance greater than many entire countries. Lightning can and does strike the same place more than once. The old saying that lightning never strikes twice is completely wrong. Tall structures are struck repeatedly because they offer a preferred path for the discharge. The Empire State Building is hit roughly 20 to 30 times each year, and the workers inside have grown so accustomed to the jolts that they barely notice anymore. Lightning rods and communication towers are designed specifically to attract strikes, because the same elevated point will be hit again and again. Lightning follows the path of least resistance, and a tall, conductive object provides a more efficient route than open air. Trees standing alone in fields bear the scars of dozens of past strikes, their bark stripped and branches twisted by repeated encounters with the sky. A place that has been struck before is more likely, not less, to be struck again. Familiarity breeds return. Lightning begins invisibly. A stepped leader descends before the flash. The flash you see during a storm is actually the final act in a sequence beginning invisibly within the cloud. A faint surge of negative charge called a stepped leader descends from the cloud base in branching segments of roughly 50 meters, each step taking about a millionth of a second. The leader is too dim to see, branching in many directions as it probes for the most efficient path to the ground. As it nears the surface, positively charged streamers rise from tall objects below. When a streamer connects with the leader, the circuit completes, and a massive return stroke surges upward in a blinding flash. What appears instantaneous is the culmination of a careful, invisible approach. And as you rest with these thoughts, there is no need to hold onto any of them. Let them pass through you like the low rumble of distant thunder, gently fading into silence. Take a breath if you wish, and let your body settle a little deeper. Ball lightning remains one of the great mysteries of atmospheric science. For centuries, people have reported luminous orbs, roughly the size of a grapefruit, floating through the air during thunderstorms. These glowing spheres, known as ball lightning, have been described hovering silently, passing through walls, and vanishing with a pop or a bang. Despite thousands of eyewitness accounts, ball lightning has proven extraordinarily difficult to study because it appears so rarely and briefly that capturing it with instruments is nearly impossible. Several theories have been proposed, from burning vaporized silicon to microwave radiation trapped in a plasma shell, but none is universally accepted. In 2014, Chinese scientists captured what may be the first confirmed spectrum of natural ball lightning. The mystery endures, a luminous riddle floating through history. Red sprites flash above thunderstorms, reaching 90 kilometers high. High above the tops of thunderstorms, at altitudes between 50 and 90 kilometers, enormous flashes of red light sometimes bloom in the darkness. These are sprites, massive discharges triggered by powerful lightning below. First photographed from an aircraft in 1989, a single sprite can extend over 50 kilometers in height, larger than the storm that created it. They last only milliseconds, but high-speed cameras reveal intricate branching structures resembling jellyfish. Sprites are caused by the temporary change in the electric field above a storm following a strong positive lightning stroke. They do not reach the ground and pose no direct danger, but they reveal that the electrical influence of a thunderstorm reaches far higher than anyone once imagined. The storm below speaks, and the sky above answers. Blue jets shoot upward from thunderclouds into the stratosphere. While sprites form high above the storm, blue jets emerge directly from cloud tops, shooting upward at roughly 100 kilometers per second in narrow, cone-shaped beams of blue light. First documented in 1994, they are thought to be caused by strong electrical fields at the very top of the thundercloud. Unlike sprites, blue jets originate within the cloud itself and propagate upward without requiring a preceding lightning flash. They typically reach altitudes of 40 to 50 kilometers, though a variant called a gigantic jet can extend to the ionosphere, nearly 100 kilometers up. These upward-reaching discharges have transformed our understanding of the atmosphere above a thunderstorm, which is far more active than it appears from below. St. Elmo's fire is a ghostly glow that appears on ships during storms. Sailors have described it for centuries, a ghostly blue or violet glow on ship masts and rigging during stormy weather. St. Elmo's fire, named after the patron saint of sailors, occurs when the electrical field around a pointed object becomes strong enough to ionize the surrounding air. The ionization creates a coronal discharge, a steady, hissing glow of plasma along the surface without a full lightning strike. It is not fire and not dangerous in itself, but it signals heavy atmospheric charge and an imminent lightning strike. Pilots have reported it dancing across windscreens and wingtips of aircraft in electrically active clouds. It is a soft brush of light hinting at the immense electrical tension building within the storm. Volcanic eruptions generate their own lightning as ash collides within the plume. When a volcano erupts, it sends a towering column of gas, rock fragments, and fine ash into the atmosphere. Within this turbulent plume, ash particles collide at tremendous speeds, stripping electrons and creating regions of charge separation much like those inside a conventional thundercloud. When the charge difference becomes large enough, lightning arcs through the plume in brilliant flashes. This phenomenon has been observed during eruptions worldwide, from Pinatubo to Eyjafjallajökull. The lightning can be extraordinarily intense, with hundreds of flashes within minutes. It is one of nature's most dramatic sights, a meeting of geological and atmospheric forces producing something rarely seen elsewhere. Fire and electricity, born from the same eruption, illuminate the sky together. Dark lightning is an invisible burst of gamma radiation inside thunderstorms. In the early 2000s, scientists discovered that thunderstorms produce brief, intense bursts of gamma radiation, the most energetic form of light. These terrestrial gamma-ray flashes are generated when powerful electric fields within a storm accelerate electrons to near light speed, producing a cascade of gamma rays lasting only a millisecond. Nicknamed dark lightning because it is invisible to the eye, the phenomenon was first detected by satellites designed to monitor gamma rays from deep space, which found the signals coming from Earth's thunderstorms. Passengers on aircraft flying through the upper reaches of a storm could theoretically receive a small radiation dose, though the risk is considered extremely low. The storm has a hidden voice only instruments can hear. Fulgurites are glass fossils of lightning frozen in the earth. When lightning strikes sand, the intense heat of roughly 30,000 degrees fuses the grains almost instantaneously, creating a hollow, branching tube of glass that follows the exact path the charge took through the ground. These fulgurites, from the Latin for thunderbolt, can extend more than 5 meters below the surface, twisting in shapes that mirror the chaotic path of the lightning. The outer surface is rough and sandy, while the inner wall is smooth and glassy, sometimes lined with delicate bubble-filled textures. Each fulgurite is unique, a fossil of a lightning strike preserved in glass. Some found are thousands of years old, silent records of ancient storms. They are the footprints of lightning frozen in the earth. And from the fierce light of lightning, we turn to a force that tears across the land with a fury all its own. A tornado can form in minutes and vanish just as quickly. Tornadoes are among the most violent and short-lived phenomena in meteorology. They form when a column of rapidly rotating air extends from a thunderstorm's base and contacts the ground. The process can unfold in minutes, beginning with a rotating updraft within a supercell that tightens into a faster, narrower vortex as it descends. Once the funnel touches the surface, it can persist from seconds to over an hour, though most last less than 10 minutes. Some carve a path only meters wide, while others leave devastation several kilometers across. Their behavior is notoriously unpredictable. They can change direction, lift off and touch down again, or split into multiple vortices. Each tornado follows its own rules. The fastest tornado winds ever recorded exceeded 480 kilometers per hour. On the 3rd of May, 1999, a violent tornado swept through suburban Oklahoma City, and a mobile Doppler radar measured wind speeds exceeding 480 kilometers per hour, among the highest ever observed in any weather event on Earth. At such velocities, the wind strips bark from trees, scours pavement from roads, and reduces buildings to foundations in seconds. The enhanced Fujita scale rates the strongest tornadoes as EF5, with winds above 320 kilometers per hour, but direct measurements are rare because most instruments cannot survive inside a violent vortex. The 1999 event gave scientists a humbling glimpse into the sheer ferocity the atmosphere can produce. Tornado Alley in the central United States experiences more tornadoes than anywhere else on Earth. A broad region stretching from northern Texas through Oklahoma, Kansas, and Nebraska is known as Tornado Alley, producing more tornadoes per year than anywhere on the planet. Warm, moist air from the Gulf of Mexico flows northward through the Great Plains and meets cold, dry air from Canada and the Rockies. This collision, combined with strong wind shear that twists updrafts into rotating columns, creates ideal conditions for supercell thunderstorms, the type most likely to produce dangerous tornadoes. The flat terrain offers no barriers, allowing storms to grow to enormous size across the endless horizon. During spring and early summer, dozens of tornadoes can occur in a single day, sometimes producing outbreaks across multiple states simultaneously. It is one of the most volatile meteorological regions on Earth. Waterspouts are tornadoes that form over water, and they can sometimes drift onto land. A waterspout is a rotating column of air extending from a cloud base to the water surface. Fair-weather waterspouts, the most common type, form over warm, shallow waters when rising moist air develops rotation from small-scale wind patterns near the surface. They are typically weaker than land tornadoes and dissipate quickly over land. However, tornadic waterspouts, spawned by the same supercells that produce land tornadoes, can be just as violent. When a waterspout moves onshore, it is reclassified as a tornado and can cause significant damage. Waterspouts are most frequent in tropical and subtropical waters, though they occur on lakes as well. A spiraling column of mist descending from a dark cloud to the sea is one of weather's most striking images. Some tornadoes are completely invisible until they pick up dust or debris from the ground. The rotating column of air that defines a tornado is itself transparent, containing nothing visible until it encounters material that can be lifted. Over clean grassland or pavement, a tornado can be entirely invisible, detectable only by the roar of the wind or the way the clouds dip and swirl. It is only when the vortex reaches loose soil, sand, or debris that it becomes visible as a darkened funnel. Some tornadoes over dark soil appear nearly black, while others passing over light earth look pale and ghostly. The color is determined entirely by what the vortex picks up, not by any quality of the wind itself. This makes tornadoes particularly dangerous in low-contrast areas where they may arrive with almost no warning. Multiple vortex tornadoes contain several smaller whirls rotating within the main funnel. Some of the most violent tornadoes contain two or more smaller vortices spinning rapidly around each other within the larger circulation, creating especially unpredictable and dangerous conditions for anyone in their path. These suction vortices rotate around the parent tornado like planets orbiting a star, producing wind speeds significantly higher than those in the broader funnel. The damage patterns are distinctive, showing narrow streaks of extreme destruction separated by lesser damage as each subvortex carves its own path through homes and trees. The interaction between subvortices and the parent circulation is complex. They can merge, split, and reform within seconds with no warning. Multiple vortex tornadoes explain some of the most puzzling surveys, where one house is completely destroyed while its neighbor stands largely intact. It is chaos within chaos. An approaching tornado sounds like a freight train that never passes. Survivors almost universally describe a deep, continuous roar that grows steadily louder as the vortex approaches, a sound unlike anything they have ever heard before. The freight train comparison captures the relentless, rumbling quality of it. This sound is produced by the tornado's winds interacting violently with the ground and objects in its path, the cracking of timber, grinding of debris, and howl of air forced through gaps in structures. Beneath this audible roar is a low-frequency infrasound generated by the vortex itself, which researchers are now exploring as an early detection tool, since these waves can travel long distances ahead of the storm. The sound of a tornado is unmistakable, a deep wall of noise that seems to press physically against the body. Tornadoes have been known to carry objects hundreds of kilometers from their original location. The extreme updrafts and winds within tornadoes can loft objects to astonishing heights and carry them great distances. Personal items, papers, and photographs have been found hundreds of kilometers away, deposited in fields or draped over fences in towns never touched by the storm. Families have received handwritten letters, children's drawings, and wedding photographs carried by the wind from communities they had never heard of, delivered by violence into quiet, untouched places. In one case, a cancelled check traveled over 300 kilometers. Heavier objects like roofing and vehicles can be carried several kilometers. The distribution patterns offer clues about the vortex's internal structure and wind speeds. Some debris is lofted into the thunderstorm itself, detectable on radar as a debris ball. The reach of a tornado extends far beyond the visible funnel, carrying fragments of one life into the hands of another. Where tornadoes carve narrow paths of chaos, rain can drown entire landscapes in a slow, relentless flood. A single large thunderstorm can release more than 10 billion liters of water in 1 hour. The water contained within a fully developed thunderstorm is almost beyond comprehension. As warm, moist air rises into the cloud, its vapor condenses into droplets and ice crystals, and when these grow heavy enough to overcome the updrafts, they fall as rain or hail. In a large storm, the total precipitation released in a single hour can exceed 10 billion liters. This water was gathered through evaporation over a vast area, sometimes traveling hundreds of kilometers before being released all at once. When so much falls in so little time, the ground cannot absorb it and drainage systems overflow. What began as invisible moisture becomes a torrent. A storm is a dam made of air, and when it breaks, the release is overwhelming. Monsoons deliver most of a year's rainfall to billions of people across 3 continents. The word monsoon comes from the Arabic for season, describing a large-scale reversal of wind direction occurring predictably each year. During summer, land masses heat up faster than surrounding oceans, creating low-pressure zones that draw in warm, moist ocean air from across thousands of kilometers. As this air rises over land, it releases its moisture in prolonged, heavy downpours lasting weeks or even months. The Indian monsoon alone provides roughly 70 to 80% of the country's annual rainfall, essential to agriculture and the livelihoods of well over 1 billion people. When it arrives late or delivers less rain than expected, the consequences include drought, crop failure, and widespread economic hardship. In winter, the pattern reverses as dry continental air flows seaward. The monsoon is a rhythm, a seasonal breath of the planet, as reliable as the turning of the year. The smell of rain on dry earth comes from a bacterial compound called geosmin. Almost everyone recognizes the fresh, earthy fragrance rising from the ground after the first rain following a dry spell. This scent is called petrichor, coined in 1964 from Greek words for stone and divine blood. The primary compound responsible is geosmin, produced by soil bacteria called actinomycetes. When raindrops hit the soil, they release tiny aerosol particles carrying geosmin into the air. The human nose detects geosmin at concentrations as low as 5 parts per trillion, a sensitivity that may have evolutionary roots, helping our ancestors sense approaching rain in arid environments. Petrichor is the smell of the earth sighing with relief, a fragrance written by bacteria and delivered by the rain. Flash floods kill more people worldwide than any other weather event. Flash floods develop with terrifying speed, often within minutes of the rainfall causing them, and are responsible for more weather-related deaths globally than hurricanes, tornadoes, or lightning. They occur when intense rainfall overwhelms the ground's absorption capacity, sending fast-moving water surging through valleys, canyons, and urban areas. The danger is amplified because floods can occur far from the rain that produced them, as water rushes downhill through channels that may be dry and sunny when the flood arrives. In narrow canyons, water can rise several meters in minutes. Even shallow flowing water can knock a person off their feet. Flash floods are a sobering reminder that the storm's most dangerous part is not always where the storm is. Supercells are rotating thunderstorms that produce the most violent weather on Earth. A supercell is defined by a deep, persistently rotating updraft called a mesocyclone. While ordinary thunderstorms collapse within an hour, a supercell sustains itself for many hours because the rotation separates the updraft from the downdraft, preventing the storm from choking itself off. This allows it to ingest warm air continuously while expelling cooled, rain-laden air to the side. Supercells produce nearly all violent tornadoes, the largest hailstones, and some of the most extreme rainfall on record. On radar, they often display a distinctive hook echo warning of tornado potential. Storm chasers describe the sight of a supercell's rotating updraft base, dark and sculpted like a living creature, as one of the most awe-inspiring spectacles in nature. To witness a supercell from a safe distance is to see the atmosphere at its most organized and menacing. Microbursts produce winds as powerful as tornadoes from a single sudden downdraft. A microburst is a concentrated column of sinking air that descends from a thunderstorm and strikes the ground with violent force, spreading outward with winds exceeding 170 kilometers per hour, strong enough to flatten trees and damage buildings in seconds. Dry microbursts produce little rain and can strike without warning from seemingly benign storms, making them particularly treacherous for pilots and anyone caught unaware. Wet microbursts bring intense rainfall alongside the devastating wind. The aviation industry became acutely aware of the threat following deadly accidents in the 1980s, where aircraft encountered sudden downbursts during landing. Airports now use specialized radar and wind shear detection to identify microbursts in real time. The storm sometimes delivers a sudden, punishing blow of air from above. Derecho storms travel in straight lines and flatten entire forests in their path. A derecho is a long-lived windstorm associated with a fast-moving band of severe thunderstorms. Unlike tornado winds, derecho winds blow in a straight line, sweeping across landscapes in swaths over 400 kilometers long with gusts exceeding 100 kilometers per hour. These storms typically develop along strong cold fronts or within mesoscale convective systems. The damage can be catastrophic, with forests blown flat in a single direction like wheat pressed by an enormous hand, power lines downed across entire regions, and structures destroyed. Because they move quickly, they catch communities off guard, arriving faster than most people can seek shelter. The 2012 North American derecho affected millions, leaving some without power for over a week in summer heat. Not all destructive wind needs to spin. Sometimes the straight path is the most devastating of all. There is something about the sound of a storm that reaches deep into the human mind. The sound of rain has been shown to lower heart rate and reduce anxiety in clinical studies. Clinical research confirms what instinct has long suggested, that the sound of rainfall has a measurable and significant calming effect on the human body. Studies have shown that exposure to rain sounds can lower heart rate, reduce blood pressure, and decrease levels of cortisol, the hormone most closely associated with stress. Rain is a form of pink noise, in which lower frequencies are slightly louder than higher ones, creating a warm, enveloping quality that the brain finds deeply soothing. Rain sounds effectively mask the sudden sharp noises that might otherwise trigger the brain's alerting systems, creating a stable acoustic environment conducive to relaxation and sleep. From an evolutionary perspective, steady rain may have signaled safety, as predators were far less active during storms. Perhaps this is why falling asleep to the sound of rain pattering against a window feels so deeply, instinctively right. The storm outside becomes a lullaby. Thunder masks distracting noises, helping many people sleep more deeply. Thunder operates in the low-frequency range of human hearing, producing deep, resonant rumbles that fill a room and effectively block the sharper, intrusive sounds that typically disturb sleep, such as traffic, voices, or household noises. This masking effect creates a uniform sound environment that helps the brain settle into deeper, more restorative rest. Beyond the acoustics, there is a powerful psychological component. The sense of being safely sheltered indoors while a storm rages outside produces a particular comfort, a feeling of enclosure and protection that many people find profoundly relaxing. Researchers have found that people fall asleep more quickly during storms and wake less frequently throughout the night. The storm becomes a guardian of sleep. Your body hears the thunder and understands, at some deep level, that the world is busy elsewhere. Astrophobia, the fear of storms, is among the 10 most common phobias in the world. While many find storms soothing, for others the experience is one of genuine terror. Astrophobia, the intense and persistent fear of thunder and lightning, is one of the 10 most common phobias in the world, particularly prevalent in children, though many adults carry it quietly throughout their entire lives. Symptoms range from mild unease to full-blown panic attacks, accompanied by rapid heartbeat, trembling, nausea, and an overwhelming urge to seek immediate shelter. The origins likely lie in a perfectly reasonable survival instinct. Early humans who sought shelter at the first signs of a storm were simply more likely to survive. In some individuals, however, this protective instinct is amplified far beyond its useful function, becoming a source of significant distress. Treatment through gradual exposure therapy and cognitive behavioral techniques has proven remarkably effective. Fear and fascination often share the same deep root. Let your breathing soften for a moment. You do not need to follow these facts anywhere. They will find their own way through you, carried on a current as steady as rainfall. Let your muscles loosen and allow yourself to drift a little further into rest. A hurricane can span over 1,000 kilometers and persist for weeks. A fully developed hurricane is one of the largest structures in the atmosphere, a spiraling mass of cloud, wind, and rain stretching more than 1,000 kilometers across. From space, it appears as a vast white pinwheel with a dark eye at its center. These storms form over warm tropical waters where the sea surface provides constant heat and moisture. Once established, a hurricane can persist for days or weeks, traveling thousands of kilometers before making landfall or encountering cooler waters that weaken it. The lifespan depends on a delicate balance of atmospheric conditions. Even small changes in wind patterns or sea temperature determine whether the storm strengthens or fades. A hurricane is a sustained process, a slow-turning engine fueled by the sea. The eye of a hurricane is calm and clear, surrounded by the most violent winds. At a hurricane's center lies the eye, a roughly circular area of calm and often clear sky, 30 to 60 kilometers across. Within it, the air descends slowly, suppressing cloud formation and sometimes revealing blue sky or stars overhead, while chaos swirls just beyond. The temperature is warmer because sinking air compresses and heats. But this calm is deceptive, for just beyond lies the eye wall, a towering ring of thunderstorms containing the highest winds, heaviest rainfall, and most violent turbulence. Those who have experienced the eye's passage describe an eerie silence amid destruction. A brief interlude before the storm's back half arrives with renewed fury, sometimes stronger than the first. The eye is the still center of a raging world. Hurricane intensity is measured on the Saffir-Simpson scale, from 1 to 5. The Saffir-Simpson scale classifies hurricanes by maximum sustained winds. Category 1 produces winds of 119 to 153 kilometers per hour, damaging roofs and downing trees. Category 2 brings winds up to 177 kilometers per hour, capable of causing extensive structural damage. Categories 3 through 5 are major hurricanes, with Category 5 exceeding 252 kilometers per hour and causing catastrophic destruction that can leave entire communities unrecognizable. Developed in the early 1970s by Herbert Saffir and Robert Simpson, the scale does not account for rainfall, surge, or tornadoes, which can be equally dangerous. Despite its limitations, it remains the standard tool for communicating hurricane intensity and guiding preparedness decisions. The deadliest cyclone in history killed over 300,000 in 1970. On the 12th of November, 1970, a massive cyclone drove a storm surge estimated at over 10 meters across the flat, densely populated river deltas of East Pakistan, now Bangladesh. Estimates of the dead range from 300,000 to 500,000, making it the deadliest tropical cyclone in history. The devastation was compounded by inadequate warning systems and the extreme vulnerability of millions living on islands barely above sea level. The aftermath fueled political anger and a sense of abandonment that contributed directly to the independence movement and the creation of Bangladesh the following year. A single storm reshaped national borders, a reminder of the immense power weather can exert over human history. Hurricanes, typhoons, and cyclones are identical storms with different regional names. The names change, but the underlying phenomenon is exactly the same. In the Atlantic and northeastern Pacific, it is called a hurricane, in the northwestern Pacific a typhoon, and in the Indian Ocean and South Pacific a cyclone. All are warm-core, low-pressure systems sustained by the evaporation of warm ocean water, sharing the same fundamental anatomy of rotating thunderstorms spiraling around a central eye. The classification threshold is identical everywhere. A tropical system becomes a hurricane, typhoon, or cyclone once its sustained winds exceed 119 kilometers per hour. Understanding that these are the same phenomenon under different regional names reveals the truly global nature of tropical storms. The oceans do not recognize the labels we give their creations. Storm surge often causes more damage than hurricane winds themselves. When a hurricane approaches a coastline, low atmospheric pressure and sustained winds push an enormous mound of water ahead of it, sometimes building for hours before landfall and arriving with terrifying speed. This storm surge can raise sea level by several meters, sending water surging inland and flooding everything in its path without mercy. In many hurricanes, the surge causes greater loss of life and property than the wind itself. It is most dangerous where coastal waters are shallow and terrain low-lying, extending floodwater kilometers inland, drowning communities built too close to the sea. Buildings are battered not only by water, but by the debris it carries, cars and timber, and everything the flood encounters. Surge coinciding with high tide can be dramatically more devastating. Many of history's deadliest hurricanes owe their toll not to the wind, but to the sea. A single hurricane releases more energy in a day than the US consumes in a year. The heat energy released through condensation in a mature hurricane equals roughly 200 times the total electrical generating capacity of the entire world. Even the kinetic energy of the winds alone equals about half the world's total electricity production. All the energy consumed in the United States in a full year, from every power plant, vehicle, factory, and household combined, is still less than what a single hurricane releases in just one day of activity. This staggering energy comes from the warm ocean surface, an almost limitless heat reservoir drawn upward through evaporation and converted into the motion of wind and the weight of precipitation. A hurricane is one of the most powerful engines in the natural world, fueled by nothing more than warm water and the turning of the sky. Hurricanes rotate anti-clockwise in the northern hemisphere and clockwise in the southern hemisphere. The Coriolis effect determines every hurricane's spin direction. In the northern hemisphere, air rushing toward the low-pressure center is deflected to the right, producing the characteristic anti-clockwise rotation visible from space. In the southern hemisphere, deflection is to the left, resulting in clockwise spin. No hurricane in the northern hemisphere has ever been observed rotating clockwise, and none in the southern has ever spun anti-clockwise. This symmetry is absolute and unbroken, a rule as reliable as gravity, written into the physics of a spinning world. Near the equator, where the Coriolis force is negligible, tropical cyclones rarely form because there is insufficient deflection to organize the converging winds into a coherent spiral. The planet turns, and the storms turn with it, forever bound to the rotation of the world beneath them. And as these great spirals of wind churn across warm oceans, the tropics give rise to storms of breathtaking scale. Typhoon Tip is the largest tropical cyclone ever recorded, spanning over 2,000 kilometers. In October of 1979, a reconnaissance aircraft flew into Typhoon Tip in the northwestern Pacific and recorded the lowest sea level pressure ever observed in a tropical cyclone, 870 millibars, a number that stunned forecasters and remains unmatched. Tip circulation stretched over 2,200 kilometers across, covering an area larger than the entire continental United States and visible from space in stunning detail. Despite its extraordinary size, it weakened considerably before making landfall in Japan, though it still caused significant flooding and loss of life. Tip demonstrated that the atmosphere can organize itself into structures of almost unimaginable dimensions, fueled entirely by the warmth of the tropical sea beneath it. It remains the benchmark against which all other tropical storms are measured. Tropical storms receive their names from rotating lists maintained by international meteorological organizations. Each ocean basin has its own list of names, cycled alphabetically each season and reused every 6 years unless a storm causes exceptional damage. Names alternate between male and female, chosen to reflect cultures of affected countries across the many regions where tropical storms form. When a storm causes exceptional damage, its name is retired and replaced, ensuring it is never used again and preserving the memory of what was lost. Retired names like Katrina, Sandy, and Haiyan are permanent markers of devastation, their power immortalized in the collective memory of nations that endured their fury. The practice began informally in the 19th century, when Caribbean meteorologists assigned saints' names to storms on whose feast days they struck. names are practical, making it far easier for families, emergency responders, and coastal communities to communicate when multiple systems are active simultaneously. A name transforms abstract coordinates into something personal, something to prepare for. Storm naming began during the Second World War to track multiple storms at once. During the Second World War, military meteorologists tracking several Pacific storms simultaneously began assigning them personal names to avoid confusion. Young radio operators, exhausted from hours of plotting storm positions, found that calling a distant typhoon Nancy or Karen made it easier to remember and communicate than latitude and longitude alone. After the war, the tradition was formalized, and by the early 1950s, a standardized list of female names was used for Atlantic hurricanes. In 1979, male names were added in alternating sequence. Naming transformed public response to weather warnings because a named storm feels more tangible and urgent than coordinates on a chart. It gave each storm an identity, and with that came greater willingness to prepare. What began as a wartime shortcut became one of the most effective tools in weather communication. A tropical depression becomes a tropical storm when its sustained winds exceed 63 kilometers per hour. The life cycle of a tropical cyclone begins as a cluster of thunderstorms over warm water, classified as a tropical disturbance. If it develops a closed circulation, it becomes a tropical depression. When sustained winds reach 63 kilometers per hour, it is reclassified as a tropical storm and named, suddenly becoming something that coastal communities begin to watch with growing attention. Not all tropical storms continue intensifying. Many weaken before reaching hurricane strength, torn apart by wind shear, starved of warm water, or disrupted by unfavorable conditions. Those that grow must maintain access to warm ocean water, low wind shear, and sufficient distance from the equator. The classification provides a common language for each stage of a storm's development, a shared vocabulary that helps millions of people prepare for what may come. Eye-wall replacement cycles cause hurricanes to weaken temporarily before potentially growing even stronger. In very intense hurricanes, a new outer eye wall sometimes forms concentrically around the original. As this outer ring strengthens, it chokes off the warm air supply feeding the inner eye wall, which gradually weakens and collapses. During this transition, the hurricane temporarily loses peak intensity, sometimes dropping an entire category. However, once the replacement cycle is complete, the outer ring often contracts and strengthens rapidly, and the storm can emerge even more powerful than before. This process can repeat multiple times during a hurricane's life, causing intensity to fluctuate unpredictably. It challenges forecasters because a seemingly weakening hurricane may in reality be undergoing internal reorganization. The storm rebuilds itself from within, dismantling its own heart to construct a new one. Rain bands produce heavy weather hundreds of kilometers from a hurricane's eye. Radiating from a hurricane's center, like spiral arms, are long, curving bands of thunderstorms called rain bands. These can extend hundreds of kilometers from the eye, producing heavy rain, strong winds, and localized tornadoes well ahead of the core, giving people their first taste of the approaching system. Rain bands form as warm, moist air flows inward toward the storm's low-pressure center, rising and condensing into towering clouds in organized, spiraling lines. The weather within these bands shifts rapidly, alternating between intense squalls and brief periods of calm as each band passes overhead. For communities in the path of an approaching hurricane, the rain bands are often the first tangible evidence of the storm's arrival, bringing deteriorating conditions hours before the core itself reaches them. Tropical cyclones weaken rapidly over land, starved of the warm ocean that fuels them. A tropical cyclone draws its energy from the evaporation of warm seawater, which sustains its towering updrafts, torrential rain, and howling winds that can devastate entire coastlines. When it moves over land, it is abruptly cut off from this fuel supply, and friction with the rough terrain disrupts its carefully organized circulation almost immediately. Most hurricanes lose their tropical characteristics within a day or two of landfall, degenerating into remnant low-pressure systems that may still bring flooding rains but lack the concentrated fury of the original storm. Similarly, passing over cooler water reduces evaporation and steadily weakens the storm from below. This is the hurricane's defining paradox. One of the most powerful forces in nature depends entirely on a thin layer of warm water to survive. Remove the warmth, and the storm dissolves into memory. But not all storms carry rain. Some arrive wrapped in white and bitter cold. A blizzard is defined by high winds and low visibility, not snowfall. The word blizzard conjures images of heavy snowfall, but the official definition focuses on the wind and what it does to visibility rather than precipitation amount. A blizzard must produce sustained winds or gusts of at least 56 kilometers per hour and reduce visibility to less than 400 meters for at least 3 hours. These conditions can occur without fresh snowfall, as winds lift previously fallen snow into a blinding wall that seems to erase the world itself, leaving only swirling white in every direction. The wind transforms ordinary snow into a disorienting environment where visibility, navigation, and survival are all compromised, where familiar landscapes vanish in moments. Wind chill can plummet to levels causing frostbite in minutes, and the cold penetrates clothing that would feel adequate on a calm day. A blizzard is measured not by the snow it drops, but by the chaos it creates. The Great Blizzard of 1888 killed over 400 people. In March of 1888, a colossal storm struck the northeastern United States with almost no warning, dumping over a meter of snow and producing hurricane-force winds that sculpted drifts as high as 15 meters. The storm paralyzed the region, trapping trains in their tracks, toppling telegraph lines, and stranding thousands in the bitter cold. Families awoke to find their doors blocked by snow taller than a man, while those caught outside struggled to find their way even across familiar streets. More than 400 people perished, many freezing to death just meters from safety they could not see. The blizzard exposed the vulnerability of above-ground infrastructure and directly inspired underground telegraph and telephone lines, as well as the New York subway system. It remains one of the most significant winter storms in American history, a reminder that even advanced civilizations can be humbled by weather. Ice storms coat everything in clear ice when rain falls through freezing air. An ice storm develops when warm air aloft produces rain that falls through a shallow layer of freezing air near the ground. The drops remain liquid during their brief passage through the cold, but solidify instantly upon contact with any freezing surface, coating everything in transparent glaze that clings and thickens with each passing hour. Trees, power lines, and roads are encased in ice that grows thicker by the hour, transforming familiar landscapes into glittering, treacherous sculptures. A single storm can deposit several centimeters, adding hundreds of kilograms to branches and power lines. The beauty is undeniable. Everything gleams as though carved from glass, catching the pale winter light in ways that feel almost enchanted. But branches snap under the weight, power lines break, and forests are transformed into landscapes of shattered crystal. Thunder snow is a rare phenomenon in which thunder and lightning occur during a snowstorm. On rare occasions, the electrical processes that produce lightning in summer storms occur within a winter storm, creating thunder snow. This requires enough convective energy, warm air rising rapidly, to generate charge separation. It typically happens when an intense winter system passes over relatively warm water, providing extra heat and moisture. Those fortunate enough to witness thundersnow describe it as one of the most surreal experiences weather can offer, standing in a world muffled by falling snow when suddenly the sky flashes white and a deep, dampened boom rolls across the frozen landscape. When lightning does occur during snow, the thunder sounds markedly different, muffled by the falling flakes and audible only within a few kilometers. The effect is eerie, a muffled boom and sudden brightening of swirling snow. Thundersnow is most common in heavy lake-effect storms and powerful nor'easters. It is winter's own kind of thunderstorm, rare and strangely beautiful. Lake-effect snow buries downwind shores as cold air absorbs moisture from warmer water. When bitterly cold air sweeps across a large body of warmer water, the temperature difference creates intense evaporation, loading the lower atmosphere with moisture. As this air reaches the far shore, it rises, cools, and condenses into thick bands of cloud that dump extraordinary quantities of snow on the land below. Residents of Buffalo know this rhythm intimately, waking to find their cars vanished beneath white drifts, while neighbors a few streets away shovel only a light dusting. Cities on the downwind shores of the Great Lakes, like Buffalo and Cleveland, can receive over 2 meters in a single event. The snow bands can be remarkably narrow, meaning one neighborhood is buried while another nearby sees only centimeters. The phenomenon requires open, unfrozen water and a significant temperature contrast, conditions most common in late autumn and early winter, when the lake still holds summer's warmth beneath winter's advancing cold. Ice storms destroy silently, their accumulating weight snapping trees and power lines. Unlike the dramatic violence of a tornado or the howling fury of a hurricane, an ice storm does its damage slowly and silently. Ice accumulates millimeter by millimeter, hour by hour, adding weight to everything it touches with a patience that is its own kind of menace. A single centimeter of ice on a power line adds more than 50 kilograms of weight per span, and when the coating reaches 2 or 3 centimeters, the combined weight is enough to snap the line or bring down the pole. Trees suffer the most visible damage, their branches pushed steadily past their breaking point by the additional burden. The sound of a severe ice storm at its peak is one of cracking and splitting as branches give way in succession across the landscape. Power outages can last weeks, affecting hundreds of thousands. The storm builds its destruction layer by layer in complete silence. Ground blizzards reduce visibility to zero without any new snowfall. A ground blizzard is deceptive and deeply disorienting. The sky may be clear and the sun shining brightly, but at the surface, howling winds lift dry snow and blow it horizontally with such force that visibility drops to near zero. No new snow is falling, yet conditions are indistinguishable from the worst blizzard. This occurs in flat, open terrain where nothing breaks the wind, allowing it to gather enormous quantities of loose snow over vast distances and whip it into a blinding wall of white. The Great Plains of North America, the Russian steppes, and polar ice sheets are common locations for these terrifying events. The disorientation can be total, roads vanish, landmarks disappear, and short distances become dangerous crossings where travelers have lost their lives just meters from safety. The storm rises from the earth. And in the driest corners of the world, storms take on a very different form. A haboob is a wall of dust over a kilometer high, traveling at 90 kilometers per hour. A haboob is born from the outflow of a collapsing thunderstorm. When the downdraft hits the ground, it spreads outward, picking up loose sand and dust in a towering wall that can stretch over 100 kilometers wide and more than a kilometer high. To witness one approaching is to see something almost biblical, a solid brown curtain advancing across the horizon, swallowing buildings and roads as it comes. The leading edge advances as a solid rolling barrier of dust, blotting out the sky and reducing visibility to nothing within seconds. Haboobs are common in the Sahara, the Arabian Peninsula, the American Southwest, and Australia. They arrive with almost no warning, transforming clear day into darkness in minutes. Behind the wall, fine particles infiltrate every crack, coating everything in grit. A haboob is the desert exhaling. Saharan dust crosses the Atlantic, depositing African soil on Caribbean beaches. Every year, roughly 180 million tons of dust are lifted from the Sahara and carried westward by trade winds across the Atlantic, more than 5,000 kilometers. If you have ever noticed a milky haze over the Caribbean sky in summer, or found a thin film of reddish dust on your car after a seemingly clear day, you may have witnessed the arrival of African soil. This Saharan air layer deposits mineral particles and iron oxides that enrich the Amazon rainforest soil with scarce nutrients, particularly phosphorus, keeping one of the most biodiverse places on Earth alive with minerals from a desert and ocean away. Satellite imagery captures these vast plumes like a translucent curtain drawn over the ocean. The dust also plays complex roles in climate, absorbing and reflecting sunlight, suppressing tropical storm formation by drying the atmosphere and seeding clouds. The Saharan dust bridges two continents, carrying the essence of one to nourish another. Sandstorms have buried entire ancient cities, erasing civilizations from the earth. Throughout history, wind-blown sand has swallowed settlements, temples, and cities, covering them so thoroughly they were lost for centuries before being rediscovered by curious archaeologists. The ancient Egyptian city of Thinis is believed to lie buried beneath desert sands, its exact location still unknown. Along the Silk Road, trading posts were gradually abandoned as dunes encroached upon walls and fields, forcing merchants to find new routes. The process is rarely sudden, more often a slow generational suffocation as sand fills streets and rises above rooftops. Some buried cities have been rediscovered, their preserved structures emerging after millennia of concealment beneath the golden grains. These places are extraordinary windows into the past. The storm that buried them was not a single event, but a slow patience, the desert reclaiming what was built on its surface. You have been resting here for a while now, and that is a good thing. There is nowhere else to be. Let each breath come a little more slowly than the last, and feel whatever stillness is gathering around you. You are doing beautifully. The Great Storm of 1703 killed over 8,000 in Britain. In late November of 1703, a ferocious cyclone struck southern England with winds that uprooted thousands of trees, unroofed buildings, and demolished the original Eddystone lighthouse, killing its designer and the men sheltering inside. At sea, hundreds of ships were sunk, and roughly 1,500 Royal Navy sailors perished in the churning waters. Church steeples toppled, lead roofing was rolled like parchment, and London's streets were littered with debris. Daniel Defoe published a detailed account based on eyewitness reports, creating one of the earliest works of modern journalism. The death toll across England, Wales, and the surrounding seas exceeded 8,000. The Great Storm remains the most destructive natural weather event in British history. The Tri-State tornado carved the longest track ever recorded in American history. On the 18th of March, 1925, a single tornado carved a path across 3 American states in 3.5 hours, covering over 350 kilometers without lifting from the ground even once. It killed 695 people, injured thousands more, and erased entire communities from the map. Its forward speed at times exceeded 100 kilometers per hour, giving people almost no time to react or find shelter. Murfreesboro, Illinois, suffered the highest death toll of any single city struck by a tornado in American history, with buildings reduced to splinters and rubble. The tornado's width exceeded 1.5 kilometers at points. The Tri-State tornado remains the deadliest single tornado in United States history, a record that has stood for a full century. The 1935 Labor Day hurricane was the first Category 5 to hit America. On the 2nd of September 1935, a compact but extraordinarily powerful hurricane struck the Florida Keys with winds near 300 kilometers per hour and the lowest landfall pressure ever recorded in the Western Hemisphere at the time. The storm obliterated Islamorada, killing over 400 people, many of them war veterans working on a government road project in the scorching heat, waiting for transport that would never come. The surge, estimated at 5 to 6 meters, washed across the low-lying islands with devastating force, leaving almost nothing standing. Evacuation had been delayed, and the rescue train arrived too late, derailed by the flooding and abandoned. The Labor Day hurricane demonstrated the lethal potential of a small, intense cyclone striking a vulnerable coastline. Its legacy shaped emergency hurricane responses for decades. The Galveston hurricane of 1900 remains America's deadliest natural disaster. On the 8th of September 1900, a powerful hurricane struck Galveston, Texas, a prosperous city on a barrier island barely 3 meters above sea level. The surge submerged the entire city, destroying roughly 3,600 buildings and killing between 6,000 and 12,000 people. Galveston was a thriving port with electric streetcars and grand architecture, reduced to rubble in hours. Afterwards, the city raised its entire grade by several meters and built a massive seawall, one of the most ambitious engineering projects of the era. The Galveston hurricane remains the deadliest natural disaster in United States history, a tragedy that reshaped a city and transformed how Americans thought about coastal vulnerability. The perfect storm of 1991 merged a hurricane with an extratropical system. In late October of 1991, a nor'easter moving up the American seaboard absorbed the remnants of Hurricane Grace, creating a storm of rare intensity that meteorologists had never seen before. Enormous waves, howling winds, and coastal flooding battered the coast from Nova Scotia to Florida. The National Weather Service called it the perfect storm because multiple meteorological factors reinforced each other, producing conditions far worse than any single component could have created alone. Seas exceeded 10 meters, and the fishing vessel Andrea Gail, with 6 crew aboard, was lost somewhere in the darkness, a tragedy later immortalized in a book and film that brought the fury of the sea into the public imagination. The pattern was exceptionally rare, but served as a vivid reminder that the atmosphere is capable of combinations beyond ordinary forecasting. Mount Tambora's eruption in 1815 caused a year without a summer. In April of 1815, Mount Tambora in present-day Indonesia ejected vast quantities of ash and sulfur dioxide into the stratosphere, creating a veil that blocked sunlight around the globe. The following year became the year without a summer. Temperatures dropped across Europe and North America, summer frosts destroyed crops, and persistent cold weather produced famine and unrest. Unusual storms flooded rivers and ruined harvests. In Switzerland, the rain-soaked summer confined a group of writers to their lodgings near Lake Geneva, where Mary Shelley began Frankenstein, a novel born from a volcanic winter. Tambora demonstrated how a single geological event could alter the climate of the entire planet. The sky remembers what the Earth releases. The Bola cyclone reshaped history, killing hundreds of thousands and birthing Bangladesh. The Bola cyclone of November 1970 had consequences far beyond its immediate devastation. The government of Pakistan, based in the Western Wing, was widely criticized for a slow and inadequate response to suffering in East Pakistan. The resulting feeling of neglect deepened ethnic and political tensions, and within months, the independence movement in East Pakistan gained unstoppable momentum. In December 1971, following a war of liberation, Bangladesh was born. Historians regard the Bola cyclone and the botched response as a decisive catalyst in the breakup of Pakistan. It is one of the clearest modern examples of a natural disaster directly influencing political events. A storm that lasted a few hours changed the map of the world. The ocean, vast and open, has always been at the mercy of storms. Rogue waves, once dismissed as sailors' myths, have been scientifically measured at heights exceeding 30 meters. For centuries, sailors told stories of enormous solitary waves that rose without warning from moderate seas and vanished after striking. These accounts were dismissed as myth until 1995, when a laser sensor on the Dropner oil platform in the North Sea recorded a wave of nearly 26 meters amid 12-meter seas. This provided unequivocal proof that rogue waves are real, and studies confirmed they occur more frequently than predicted. They arise from constructive interference of multiple wave trains and can be amplified by ocean currents that compress incoming swells. Ships struck by rogue waves have suffered catastrophic damage, and some maritime losses, once attributed to other causes, are now suspected to have been caused by these events. The ocean has always been wilder than we imagined. Storm waves travel thousands of kilometers before arriving as gentle swells. When powerful winds blow across open water for an extended period, they transfer energy to the surface, building waves that grow with distance and duration. Once beyond the storm, these waves propagate as swell, losing very little energy as they travel. A swell from the Southern Ocean near Antarctica can cross 10,000 kilometers before arriving at California or Hawaii as long, smooth rollers bearing no trace of the violence that produced them. Surfers riding these swells are riding stored energy from a storm that occurred days earlier and thousands of kilometers away. The ocean is a vast conveyor of energy, delivering the power of distant storms gently to faraway shores. Every wave that reaches the beach is a message from the wind. The Beaufort scale classifies wind force from calm to hurricane strength. In 1805, Irish hydrographer Francis Beaufort devised a scale describing wind strength at sea, originally based on the effect of wind on a warship's sails. It ranges from force 0, dead calm with a mirror-smooth sea, to force 12, hurricane force winds with enormous waves and dense spray. Over time, the scale was refined with specific wind speed ranges and descriptions for land as well as sea. Force 6 describes a strong breeze with large waves, while Force 10, a full storm, produces very high waves with overhanging crests. The scale endures because of its intuitive simplicity, a single number conveying an immediate sense of the wind. It is a testament to Beaufort that his system, conceived aboard a sailing vessel 2 centuries ago, remains relevant in the age of satellites. Waterspouts can overturn boats and cause significant coastal damage. Most fair-weather waterspouts have wind speeds below 100 kilometers per hour, but they can capsize small boats and reduce visibility for anyone caught nearby. Fishermen in warm tropical waters learn to watch for the telltale signs, a dark patch on the water's surface rotating ominously beneath a low, dark cloud. In tropical regions, multiple spouts sometimes form simultaneously along a single convergence line, creating a surreal procession of funnels stretching from cloud base to sea. Sailors learn to recognize conditions favoring waterspout development, warm water, high humidity, and light variable winds. When strong thunderstorms are involved, waterspouts can approach moderate tornado intensity. The sight of a narrow, twisting column connecting a dark cloud to the ocean surface is both mesmerizing and menacing, a reminder that the sea and sky share a restless bond. The Bermuda Triangle's mysteries, are largely explained by sudden, violent storms. The western Atlantic area, known as the Bermuda Triangle, bounded roughly by Miami, Bermuda, and Puerto Rico, has long been linked to mysterious disappearances of ships and aircraft. While popular culture offers exotic explanations involving everything from magnetic anomalies to extraterrestrial intervention, the most likely cause is far more ordinary: the region's weather. Warm Gulf Stream waters and converging air masses produce waterspouts, microbursts, and rapidly developing storms with little warning. Navigational errors across the featureless ocean compound the danger. The traffic volume through this area is enormous, and when the disappearance rate is adjusted for density, it is no higher than in comparable ocean regions. The mystery is largely the product of the same forces that drive storms everywhere: warm water, unstable air, and a sky that changes its mood in minutes. Storms can raise sea levels along coastlines by several meters. When a powerful storm crosses open ocean, its sustained winds push water ahead in vast quantities, creating a storm surge, a temporary but significant rise in sea level. During tropical cyclones, low pressure and extreme winds can raise the surface by several meters. Even extratropical storms can drive substantial surges. The wind stress can alter ocean current direction and speed at considerable depth, temporarily rearranging flow across entire basins. In confined waters like the North Sea, funnel-shaped geography amplifies the effect. The 1953 North Sea flood, driven by a severe windstorm, claimed over 2,000 lives in the Netherlands and the United Kingdom. The ocean obeys the wind, and when the wind is strong enough, the sea rises. For centuries, humans could only watch storms approach and hope. Today, the science of prediction has transformed our relationship with the sky. Modern weather satellites can track the formation and movement of storms from space in real time. Since the first weather satellite launched in 1960, a constellation of geostationary and polar orbiting satellites now provides continuous, high-resolution imagery of the entire planet. Geostationary satellites hover at 36,000 kilometers, maintaining a fixed view ideal for tracking cyclones as they evolve. Polar orbiting satellites circle at lower altitudes, building a detailed global picture several times daily. Together they track cloud formations, sea surface temperatures, and atmospheric moisture in real time, providing early warning of storms that might otherwise develop undetected over remote oceans. Before satellites, a hurricane could form and intensify entirely unobserved until it struck a coastline. Today, we watch a storm from birth to death, a perspective that has saved countless lives. Doppler radar detects rotation inside storms, enabling tornado warnings. Conventional radar sends pulses of microwave energy and measures the strength of the signal that bounces back, revealing the location and intensity of precipitation. Doppler radar adds a crucial dimension by measuring the frequency shift in returning signals caused by particle motion toward or away from the antenna. This Doppler effect allows meteorologists to detect areas of rotation that may indicate a developing tornado or mesocyclone within a supercell. Dual polarization technology sends pulses in both horizontal and vertical orientations, providing information about particle shape and size, distinguishing between rain, hail, snow, and debris. The network of Doppler radar stations forms the backbone of severe weather detection, providing the data that underlies most tornado warnings and storm alerts issued today. Numerical weather prediction uses mathematical models of the atmosphere to forecast storms days before they arrive. Modern weather forecasting divides the atmosphere into a three-dimensional grid of millions of cells, each one described by variables such as temperature, pressure, humidity, and wind speed. Powerful supercomputers solve the governing equations for each cell, stepping forward in time to produce forecasts extending days or even weeks into the future. The accuracy of these forecasts has improved steadily, and today a 5-day forecast is roughly as accurate as a 2-day forecast was in the 1980s. However, the chaotic nature of the atmosphere imposes fundamental limits on predictability, and small errors in initial observations can grow rapidly over time, increasing uncertainty in longer-range predictions. Models are updated several times daily as new observations arrive, constantly refining their picture of the evolving atmosphere. Whether prediction is a race between observation and chaos. Storm chasers drive directly into severe weather to collect data. Every spring, teams of storm chasers fan out across the central United States with radar, cameras, and specialized vehicles designed to withstand hail and debris. Some are university researchers, others are forecasters, and some are passionate amateurs drawn by the spectacle of nature at its most dramatic. Their close-range measurements of wind, pressure, and humidity in and around tornadoes have been invaluable for understanding how tornadoes form, intensify, and dissipate with such sudden violence. Some deploy instruments directly in a tornado's path, racing against time and the storm itself. The risks are considerable, and several chasers have lost their lives in pursuit of data and images that might one day save others. But the data they gather has significantly improved warning systems and lead times, saving countless lives. Storm chasing is a blend of science, courage, and a deep fascination with the raw power of the atmosphere. The telegraph lets storm warnings travel faster than the storms themselves. Before the telegraph, weather warnings could travel only as fast as a person on horseback, meaning storms often arrived first, without any warning at all. The electric telegraph, developed in the 1840s, made it possible to transmit observations between cities in minutes rather than days. For the first time, a storm report from the west could reach communities in its path before the storm itself arrived. This led to the first organized weather observation networks and warning services, with observers reporting by telegraph to central offices that compiled the data into forecasts. The Smithsonian Institution pioneered this system, and by the 1860s daily, weather maps were being produced in several countries. The telegraph gave humanity something new, the ability to outrun a storm with information. Ensemble forecasting runs dozens of weather simulations simultaneously to account for the deep uncertainty in storm predictions. Because the atmosphere is a chaotic system, even tiny differences in the initial conditions used to start a weather model can lead to dramatically different outcomes over time. Ensemble forecasting addresses this challenge by running the same model many times, each with slightly varied starting conditions, to produce a range of possible outcomes rather than a single forecast. By comparing the results, forecasters can assess the probability of different scenarios, the likelihood of one hurricane path versus another, or the chance of severe hail rather than heavy rain. When ensemble members agree closely, forecasters can be more confident in the predicted outcome. When they diverge widely, it signals that the situation is highly uncertain. This probabilistic approach has become one of the most important tools in modern meteorology, providing a far more honest and useful picture of the future than any single deterministic forecast could offer. Weather prediction is not about certainty, it is about understanding what is possible. The cone of uncertainty shows possible hurricane paths, not the storm's size. When a hurricane approaches land, forecasters issue a track forecast with a cone-shaped graphic showing the range of possible future positions of the storm's center over the coming days. The cone is often misunderstood as showing the hurricane's physical size, when in fact it represents something quite different. In reality, it represents potential tracks based on historical forecast errors accumulated over decades of tropical weather prediction. Damaging winds, rain, and surge extend well beyond the center and may affect areas outside the cone. The cone widens with time as uncertainty grows with each passing hour. Over the years, it has narrowed as accuracy improved, but it remains essential for communicating uncertainty. People outside the cone are not necessarily safe, and those inside are not certain to experience the worst. The cone is a picture of possibility, not a promise. Storms are not only forces of destruction, they are woven into the very fabric of life on Earth. Many plant species depend on storms to disperse their seeds across wide areas. The powerful winds of a storm can carry seeds, spores, and pollen over distances that no ordinary breeze could ever achieve. Some species have evolved lightweight, aerodynamic seeds specifically designed to be caught and carried by strong winds, exploiting the energy of storms to colonize distant territory far from the parent plant. Dandelion seeds, maple samaras, and the feathery plumes of many grass species are shaped by evolution to ride the currents of moving air. And during storms, these mechanisms work at their maximum efficiency, dispersing seeds across entire landscapes in a matter of hours. Some tropical trees deliberately time their seed release to coincide with the seasonal storm season, ensuring their offspring are scattered as widely as possible. Floodwaters produced by storms also serve as dispersal agents, carrying seeds downstream to fertile new ground. Storms are essential partners in the reproductive strategies of countless plant species. The wind that uproots one tree carries the seeds of the next generation. Lightning-triggered wildfires play an essential role in the regeneration of certain forest ecosystems. In many regions, forest ecosystems have evolved over millions of years in the presence of periodic wildfire, and lightning is the primary natural ignition source. In boreal forests, pine savannas, and eucalyptus woodlands, fire is not an aberration, but a fundamental part of the ecological cycle. The lodgepole pine produces cones sealed by resin that remain closed for years, opening only after the intense heat of a fire melts the seal, releasing seeds onto the freshly cleared ground. Other species have thick, fire-resistant bark that protects the living tissue within. The ash left behind enriches soil with nutrients, and the removal of dense undergrowth lets sunlight reach the forest floor, promoting vigorous new growth. Without periodic fire, many of these ecosystems would become choked with dead vegetation and eventually collapse. Lightning provides the spark that keeps the forest alive. Storms churn deep ocean nutrients to the surface, feeding oxygen-producing phytoplankton. When a powerful storm passes over the ocean, the turbulence it generates extends far below the surface, mixing the upper layers of water and drawing cold, nutrient-rich water up from the depths. These nutrients, particularly nitrogen and phosphorus, fertilize the surface waters and trigger blooms of phytoplankton, the microscopic organisms that form the base of the marine food web. Phytoplankton are also responsible for producing an estimated 50 to 80% of the oxygen in the Earth's atmosphere. After a major hurricane or typhoon, satellite imagery often reveals a dramatic increase in surface chlorophyll in the storm's wake. The destructive energy of a storm is thus transformed into remarkable biological productivity, fueling the growth of the tiny organisms that sustain ocean life, from the smallest fish to the largest whale. The storm stirs the sea, and the sea responds with life. Some birds deliberately fly into hurricanes to travel vast distances with minimal effort. Seabirds such as frigate birds, shearwaters, and petrels have been tracked by satellite as they approach, and sometimes enter the spiral arms of tropical cyclones, riding the powerful winds to cover enormous distances with very little expenditure of energy. With long, narrow wings supremely adapted for soaring and gliding, they circle within the outer bands, using updrafts and tailwinds to travel hundreds of kilometers in a single day. After the storm passes, displaced birds are sometimes found far inland, hundreds of kilometers from their normal range, carried there by wind patterns they could not escape. Birdwatchers call these hurricane birds, turning violent weather events into opportunities for rare sightings of species never normally seen so far from the coast. For the birds, flying near a storm is a calculated gamble, the rewards of effortless travel balanced against the risk of being overwhelmed by wind and rain. Even in chaos, nature finds a way. Lightning fixes nitrogen into the soil, acting as a natural fertilizer. Every bolt of lightning that arcs through the atmosphere generates intense heat that causes nitrogen and oxygen molecules in the air to combine, forming nitrogen oxides. These compounds dissolve in rain and are carried to the ground, where they enter the soil as naturally fixed nitrogen, one of the most essential nutrients for plant growth. Though modest compared to bacterial and industrial sources, lightning contributes an estimated several million tons yearly to the Earth's nitrogen cycle. In remote regions where industrial fertilizers are unavailable, this lightning-fixed nitrogen can be an important source of this vital nutrient. The process has been occurring for billions of years, silently enriching the soil with every passing storm. It is a form of atmospheric generosity, the sky delivering nourishment to the ground through the same bolts that terrify and astonish. Even the most violent storms leave something behind that helps the living world grow. Let this be another moment of stillness. You do not need to carry any of these facts with you. They are here simply to keep you company as you rest. Feel the warmth of wherever you are lying and let your thoughts become as soft and distant as clouds passing overhead. Jupiter's Great Red Spot is a storm larger than Earth, raging for 3 centuries. High in Jupiter's banded atmosphere, a colossal anticyclonic storm swirls endlessly, large enough to swallow Earth with room to spare. Observed since at least the 17th century, it is the longest known storm in the solar system. Winds at its edges exceed 500 kilometers per hour, and it extends deep into Jupiter's hydrogen-rich atmosphere. The Great Red Spot has been gradually shrinking over the past century, and astronomers are uncertain whether it will disappear or stabilize. Its color, varying from brick red to pale salmon, is thought to result from complex chemical reactions, though the exact compounds remain debated. On Jupiter, a storm needs neither land nor sea. It only needs time. Saturn's North Pole has a hexagonal storm with no equivalent anywhere else. At Saturn's North Pole, a vast jet stream traces a nearly perfect hexagonal shape, each side longer than Earth's diameter, enclosing a rotating vortex that extends deep into the atmosphere. First observed by the Voyager missions in the 1980s and studied in detail by Cassini, the hexagon has persisted for decades with remarkable stability. It is thought to be a standing wave in the polar jet stream generated by the interaction of wind speeds at particular latitudes, though no model has fully reproduced its geometry. At the center lies a smaller cyclone with an eye wall resembling a terrestrial hurricane. The hexagonal storm exists where there is no land, no water, and no apparent reason for such geometric elegance. Saturn's pole is the strangest art gallery in the solar system. Neptune has the fastest winds of any planet, exceeding 2,000 kilometers per hour. Despite receiving a fraction of Earth's sunlight, the ice giant Neptune generates some of the most violent weather in the solar system. Wind speeds exceed 2,000 kilometers per hour, the fastest of any planet, and massive dark storm systems appear and disappear over months to years. The Great Dark Spot, observed by Voyager 2 in 1989, was roughly Earth-sized, but vanished within a few years, replaced by new dark spots elsewhere. The source of Neptune's extreme weather remains unclear, as the planet receives 900 times less solar energy than Earth. Internal heat rising from the core is thought to drive convection and generate the ferocious winds. Neptune is a world of howling blue darkness where the wind never rests. Mars experiences planet-wide dust storms that can last for months and completely obscure the surface from view. Every few years, the thin Martian atmosphere produces dust storms that grow from regional disturbances into global events, wrapping the entire planet in airborne particles. These storms can last months, reducing visibility to near zero and blocking enough sunlight to cripple solar-powered spacecraft. The mechanism is a positive feedback loop. Dark dust absorbs sunlight and heats the air, driving convection that lifts more dust, escalating a regional storm into a global event in days. The Opportunity rover, which operated for over 14 years, was silenced by a global dust storm in 2018 that blocked its solar panels permanently. On Mars, the dust does not merely blow across the land, it swallows the sky. Venus has permanent vortices of sulfuric acid swirling at each pole. The atmosphere of Venus is a dense, scorching envelope of carbon dioxide capped with thick clouds of sulfuric acid. At each pole, circulation converges into enormous, slowly rotating vortices visible from orbit. The South Polar Vortex, imaged by Venus Express, is a dynamic feature that can appear as a single eye or a double-lobed structure. Surface pressure is roughly 90 times Earth's, and temperatures average 460 degrees Celsius. Despite these conditions, some scientists have speculated that microbial life could exist in the more moderate upper cloud layers. The storms of Venus are unlike anything on Earth, more chemical than meteorological, a reminder that weather takes many forms across the solar system. Titan, Saturn's largest moon, experiences methane rainstorms that carve rivers and fill lakes on its frigid surface. Titan is the only body besides Earth where liquid currently flows on the surface, but the liquid is methane and ethane, cycling through an alien hydrological system at -179 degrees Celsius. Methane evaporates from vast polar lakes, rises into the thick nitrogen atmosphere, condenses into clouds, and falls as rain, carving river channels and filling basins in a cycle that mirrors Earth's water cycle. Cassini-Huygens revealed dunes, rivers, lakes, and shorelines shaped by liquid hydrocarbons. The rain falls slowly in Titan's low gravity and thick atmosphere, in large drops drifting downward, almost dreamlike. It is a world of perpetual twilight where the rivers flow with the stuff of fire. Titan reminds us that storms are a universal phenomenon. The sun produces storms that send billions of tons of plasma toward every planet. Solar storms are not storms of wind and rain, but of plasma, magnetic energy, and radiation. A coronal mass ejection occurs when the sun's magnetic field becomes unstable, releasing billions of tons of charged particles at speeds exceeding millions of kilometers per hour. When these reach Earth, they interact with our magnetic field, sometimes triggering spectacular auroras. In extreme cases, solar storms disrupt satellite communications, damage electrical grids, and pose radiation risks to astronauts. The Carrington event of 1859, the most powerful geomagnetic storm recorded, caused telegraph machines to spark and catch fire and produced auroras visible as far south as the Caribbean. The Sun, our nearest star, is also our nearest source of cosmic weather. And from the furthest reaches of the cosmos, we return to something closer, something deeply personal. Storms have inspired myth, art, music, and literature throughout human history. From the earliest cave paintings to the canvases of Turner and Constable, from the tempest-tossed verses of Homer's Odyssey to the haunting storm scenes of Shakespeare's King Lear, storms have occupied a central place in the creative imagination of humanity. Composers have sought to capture the sound of thunder in their symphonies. Beethoven's Pastoral Symphony contains a storm movement of vivid intensity, and Vivaldi's Four Seasons evokes the crackle and rumble of summer thunder with startling realism. Poets have written of storms as metaphors for inner turmoil, for transformation, for the overwhelming power of forces beyond human control. In visual art, the storm offers artists a chance to explore light, drama, and the sublime, that sensation of awe mixed with terror that the 18th century philosophers described when confronting the untamable forces of nature. In literature, the storm is often a turning point, the moment when the ordinary world is swept away and something new, uncertain, and full of possibility takes its place. Storms are not merely weather. They are stories the sky tells about the world. The word storm comes from Old English, meaning tumult or disturbance. The English word storm traces back to Old English stium, from a Proto-Germanic root meaning noise, tumult, or disturbance. It is related to the German Sturm, the Dutch storm, and Old Norse storma, reflecting a shared heritage among Northern European peoples for whom storms were a formidable presence. Across many languages, words for storm carry connotations of upheaval and sudden change, suggesting that the experience of a powerful storm has been universal since the earliest days of language. In English, the word has expanded beyond meteorology. We speak of storming a castle, a storm of protest, brainstorming. The metaphor is instinctive, rooted in the memory of thunder, wind, and rain. Language remembers the storms that shaped it. Storm deities appear in nearly every culture, from Thor to Indra to Zeus. The desire to understand and explain the terrifying power of storms has led cultures on every inhabited continent to create divinities associated with thunder, lightning, wind, and rain. In Norse mythology, Thor wielded his hammer Mjolnir to produce thunderbolts, riding across the sky in a chariot drawn by goats. In Hindu tradition, Indra was the king of the gods and lord of storms, wielding the Vajra to defeat demons and bring rain to the parched earth. The Greeks attributed lightning to Zeus, the Yoruba honored Shango, the Japanese had Raijin, and the Mesoamericans worshipped Tlaloc. The universality of storm deities is striking evidence that the experience of a thunderstorm, the flash of light, the rumble of sound, the trembling of the earth, is among the most powerful and primal experiences in human existence. Before there was science, there were stories, and in those stories the storm was always something alive, something with a will, something worthy of both reverence and fear. Storms are growing more intense due to rising global temperatures. As the Earth's average surface temperature continues to rise, driven by increasing concentrations of greenhouse gases in the atmosphere, the amount of energy available to power storms is also increasing. Warmer oceans provide more moisture and more thermal energy to developing tropical cyclones, and the proportion of the most intense hurricanes, those reaching Category 4 and 5, has grown measurably in recent decades. Warmer air holds roughly 7% more moisture for every degree Celsius of warming, which means storms of all types are producing heavier rainfall than they did in previous generations. The link between rising temperatures and storm intensity is supported by a growing body of scientific evidence. Extreme rainfall events are becoming more common in many parts of the world, leading to increased flooding and water damage. The warming of the Arctic is also altering the jet stream, potentially causing weather patterns to stall, prolonging droughts, heat waves, and excessive rainfall over the same areas for days at a time. The climate is changing, and the storms are changing with it. Storms are essential to Earth's climate, moving heat and cycling water. Storms are the atmosphere's primary mechanism for redistributing energy, carrying warm, moist air from the tropics toward the poles and balancing temperature differences. Without storms, Equatorial regions would overheat and polar regions would freeze further. The water cycle depends on storms to return moisture from oceans to land, filling rivers, recharging aquifers, and watering soil. Storms also drive ocean currents, mix atmospheric gases, clean pollutants from the air, and deliver nutrients. In forests, they create canopy gaps for new growth. In grasslands, they end droughts. In the deep ocean, they stir nutrients to the surface. The Earth without storms would be a planet without renewal. Storms are the heartbeat of the atmosphere. After every storm, the air is cleaner and the world feels made new. There is a stillness after a storm unlike any other quiet. The air, washed clean by rain, carries a freshness you can taste. The light arrives with a clarity that makes familiar landscapes look startlingly vivid. Puddles reflect the sky with the sharpness of mirrors, and leaves, rinsed and glistening, seem greener than before. Birds begin to sing, tentatively at first, reclaiming the soundscape from retreating thunder. For a few minutes, there is a profound sense of renewal, as though the storm has scrubbed the world clean and set it down slightly brighter and more alive than before. This post-storm stillness is one of the atmosphere's most gentle gifts. It is the sky's way of saying that even the most turbulent night gives way to calm. And so our journey through the world of storms draws softly to a close. We have wandered from the quiet warming of air that sets a storm in motion to the brilliant flash of lightning that splits the sky. We have stood at the edge of tornadoes and hurricanes, listened to the slow drumming of rain on dry earth, and gazed upon storms that rage on distant planets. From the smallest raindrop to the largest cyclone, from ancient tempests that reshaped nations to the silent electrical discharges flickering above the clouds, we have explored the many faces of a force that is both fearsome and beautiful. Every storm, in its own way, is a conversation between the earth and the sky, a reminder that the atmosphere is never truly still. If this journey has brought you a measure of peace tonight, I warmly invite you to subscribe or share this space with someone who might need it. There are more wonders waiting, more quiet corners of the universe to explore, one calm night at a time. Right now, as you listen, the atmosphere is still at work somewhere above you. Clouds are forming and dissolving, rain is falling on forests and distant oceans, and the great cycles of heat and moisture continue their patient turning. Your own body carries the memory of every storm you have ever witnessed, every rumble of thunder, every flash of light in a darkened sky, every drop of rain on your skin. If your eyes feel heavy, let them close. Let the last traces of tension leave your shoulders, your jaw, your hands. Breathe in slowly, and as you breathe out, imagine the stillness that follows a great storm, the silence after the last roll of thunder, the soft dripping of rain from leaves, the clearing sky revealing the first pale star. Let that deep, earned calm settle over you now, and feel your body grow heavier against the place where you rest. Tonight, as you sleep, storms continue their work across the globe. Rain is feeding rivers, lightning is enriching the soil, winds are carrying warmth from the tropics toward the poles. The atmosphere breathes, shifts, and balances itself in an endless turning of energy and air. You are a small, warm presence within this vast and restless sky, peacefully resting among the wonders. Sleep well, sweet dreams, and may you carry with you the quiet knowledge that even the most powerful storms eventually pass, and what they leave behind is a world washed clean, a sky full of stars, and the stillness that only comes after the thunder has spoken its last word. This has been Drowsy Discovery. Good night.